Hi everyone, my name is Chavoosh and I'm from University of Arizona. In this presentation, I'm going to talk about iCDN, which is a solution for building a CDN using NDN technology. Simply put, a CDN is an overlay network on top of the internet. It caches and forwards requests based on their name rather than destination's IP address. Upon receiving a request, it will try to find the content somewhere in the network, and if it could not, it will directly fetch it from the original producer. To let CDN servers find the cache contents in the network, a common solution that CDNs use is employing a third-party system module that keeps track of the in-network caches. So when a CDN service receives a request, it will ask this module that whether the content is available anywhere in the network, and if so, what server has it. The main concern with this solution is the lack of scalability that brings many resources to the system and significantly changes the design of the network. So we can ask this question that what if CDNs could find the content without relying on another system component? To put it in a different way, we're thinking about a network that can cache, find, and serve contents at the forwarding plane without a strong dependency on any controlling module. And this network needs to be highly scalable to handle millions of contents. ICN and NDN in particular seems to be able to build such a network. But the question is, does any implementation of NDN necessarily perform as a CDN? The answer is no. Just because a network uses NDN technology, it doesn't mean it can be expanded to serve as a CDN. This is because the common networking solution in NDN has scalability issues. To get a better sense of what this means, consider the NDN testbed. The testbed relies on a routing protocol to disseminate content availability information among the nodes, and this dependency raises two major issues. As the first issue, the routing protocol requires each node to keep information about each content in the network in their FIB, and combining this approach with an ever-increasing number of contents and origins in the network can rapidly lead to FIB explosion. The other issue is that the routing protocol only computes the routes from each node to the origins, and it excludes in-network caches. This makes utilizing on-path caches completely opportunistic and off-path caches impossible. Off-path caches refer to the nodes which are not on the path to the origin, but they have the content. So iCDN tries to address these two issues. More specifically, iCDN provides a new design to build a scalable and high-performance NDN-based CDN. To address FIB explosion, iCDN utilizes a full mesh network topology and builds a cache hierarchy on top of it. It also mitigates in-network caching issues by proposing a new forwarding strategy called C strategy, where C stands for CDN. But before we move forward, it's important to mention that CDNs are profoundly complex ecosystem with many different types of features and services. So we do not have any intention to replace or replicate CDN in this work in any fashion. The only aspect of CDNs that we study is the content sharing and retrieval, which is the most common feature of today's CDNs. Okay, now let's see how iCDN's network design works, and then we will discuss details of C strategy. As I mentioned, iCDN uses a full mesh network topology, just like any other overlay network. It means that there is a one-hop virtual link between any pair of nodes in this network, even if physically those nodes are multiple hops away from each other. However, in majority of CDNs, a routing module prunes the full mesh topology and tightens each node to a small set of paths. But in iCDN, each node can use any path in this full mesh topology at any given time. As another important point, iCDN logically partitions the network for management purposes. It means the administrator can group the number of nodes in the network into one partition, but a partition doesn't cut the actual access of a node to the rest of the network. On top of this network, we built a cache hierarchy to fully utilize in-network caching capability of NDN without causing FIB explosion. This figure shows how this cache hierarchy looks like. A very important point is the cache hierarchy is defined only for one namespace or content. So for the rest of the presentation, whenever I mention cache hierarchy, remember that it belongs only to one namespace. For example, here, this cache hierarchy is formed for namespace ABC, and this node is a producer of this namespace. There are three tiers in this hierarchy, and the very top tier belongs to the nodes that are responsible for caching the contents under the corresponding namespace. We call them RPs, or rendezvous point. To find RPs, we use consistent hashing, so each node hashes the name of the content or the namespace to find the RPs for that specific namespace. The second tier belongs to hot nodes. The main idea here is that in-network caches offer an excellent opportunity for a faster content retrieval. To fully utilize caches, the in-network caches, the nodes need to announce their cache contents, but we cannot ask them to announce all their contents. The key point here is that the content popularity on today's internet closely follows zip distribution, and this distribution says that the majority of requests in the network are served by a relatively small portion of contents. So we use a decay function to allow each node to choose a small set of their most requested contents as hot contents and announce them to the rest of the nodes within the partition. This announcement is a routing announcement populated within one partition. So the nodes at this tier, like node Y, believe that the contents under this namespace are popular and hot in the network. The rest of the nodes within one partition which are not RP or hot are considered as cold nodes. So based on this hierarchy, we can see that each node in one partition offers different level of guarantee of the content availability in their cache for a given namespace. And it's a job of a forwarding strategy to incorporate this information and choose like what node in this hierarchy provides the highest content retrieval performance to retrieve specific content. So this takes us to C strategy. This strategy uses the cache hierarchy and tries to exploit off-path and on-path caches in the network. When a node experiences a cache miss based on the location of that node in the hierarchy, C strategy chooses some nodes in higher tiers and probes them. For example, if the node is a hot node, C strategy chooses some nodes from RP tiers to probe, not from hot or cold tiers. After that, it tries to figure out which of the probe nodes provide better content retrieval performance to send the remaining interest to that node. To do so, C strategy uses a weighted moving average formula that includes RTT, number of NACs, timeouts, and estimated bandwidth. This strategy captures network changes by periodically periodically probing more nodes in the network. And if we found a node with significantly higher performance, it will switch to that node. To evaluate iCDN's performance, we compare it against the most common networking solution in NDN, which is using a routing protocol to populate the FIPS, and after that, using a forwarding strategy to choose the next hop from FIP at any given time. Because this solution is adopted by NDN testbed, we refer to it as the testbed solution. We compare C strategy in iCDN with ASF, best route, and flooding strategies in a testbed solution. We use NDN sim for the simulations, and the request pattern in all simulations follows zip distribution. We use Abilene topology as is shown here, and consumers are connected to nodes 0, 3, and 5. The producer is connected to node 10. Here, I'm going to present only some of the results, and you can find more results and comparisons in the paper. So this figure shows how fast node 0 downloads different contents in the network. As you can see, C strategy, which is represented by the black line, outperforms ASF and best router strategy. And the main reason here is because C strategy fully utilizes in-network caching capability of NDN in like either off-path or off-path caches. However, compared to the flooding strategy, which is represented by the blue line, we can see an interesting observation. Initially, we expected to see that flooding outperforms C strategy in all cases because it tries to maximize the cache hit ratio in the network. But except for like a few contents, we can see that C strategy shows a better performance than flooding. And that is because flooding overwhelms the network with a huge amount of requests, causing a lot of unnecessary cache eviction on each node. And also it treats all contents in the same way without giving any priority to the hot contents that are more likely to be requested in the future. In terms of being responsive to network changes, we break an important link in Abilene topology, which is shared by several paths while downloading a single content to see how fast each solution reacts to this change. This figure shows that the dependency of ASF and best route, which are represented by, if you follow the red and green lines, that dependency made these two strategies completely stop serving for a period of time, and after the routing protocol computed the new paths and updated the FIB, they started serving the content. C strategy and flooding, which are represented by black and blue lines, on the other hand, immediately switch to another path. And this is because they do not rely on a routing protocol or any centralized controlling module to find an alternative path. And actually, that is why the C strategy and flooding finished downloading this content much sooner than ASF and best route. Finally, in terms of scalability, we study iCDN and testbed solution by measuring the FIB size on node 0 while increasing the number of origins, accordingly contents in a network. By increasing the number of origins in a network, the routing protocol requires FIB on each node to store more and more information, even though a given node, in this example node 0, might never receive any request for some of the contents in the network. In iCDN, which is represented by the black line, we can see that each node's FIB is populated by hot nodes announcement. Thus, no matter how many contents the network serves, the FIB on each node keeps information of a very small group of contents at any given time, which sufficiently helps C strategy tune its forwarding decisions. So to conclude, iCDN is an exclusive network designed for large-scale content distribution using NDN technology. It builds a cache hierarchy among the network nodes and proposes a new forwarding strategy to efficiently forward packets in this hierarchy without relying on any centralized controlling module or routing protocol. The design of iCDN plus C strategy addresses FIB explosion and inefficient use of in-network caching in a network. And we do hope that iCDN builds a concrete foundation towards a complete NDN-based CDN design and performance evaluation in the future. And thank you.